But before we start today's lecture, let's look at what we did in lecture number 5. So in lecture number 5, we looked at the interference in the temporal degree of freedom. This one is the general temporal interference law. Here the main question we ask in the temporal interference is that what is the correlation between the field vibrations at 2 points that are separated in time by t2 minus t1. And the general methodology is that one picks up fields from those 2 points and then combines it through an interferometer, and then the intensity at the output port of the interferometer then contains this correlation information. So this one is the correlation between the fields at point t minus t1 and t minus t2, and then we saw that last time that the intensity at the output port of the interferometer contains the intensity coming through the first term, intensity coming through the second arm, and these have intensities at t minus t1 and t minus t2. And then there is this third term, and of course a complex conjugate, which is the correlation that contains how the field vibrations at t minus t1 and t minus t2 are correlated. So the main point here is that the intensity measurements at the detector yields the correlation information of the source. So this is the generic interference scheme, and this is the method by which one obtains the correlation information by looking at the intensity, because one can only measure the intensity as far as the measurement is concerned, but through the intensity measurement it is possible to get the information about the correlation. Okay, now this correlation in time, this temporal correlation function or the cross correlation function, this we saw that we can also study this in the frequency domain. And when we study it in the frequency domain, the function is called the cross spectral density function, and we divide the cross spectral density function in few cases. The case one was we looked at when there is no correlation between different frequency components. When there is no frequency correlation between different components, then the cross spectral density function can be written in this manner. This is the definition of the cross spectral density function. And this can be written simply as this spectral density s omega 1 and the delta function. This delta function ensures that there is correlation only when omega 1 is equal to omega 2, that means the same frequency, but if omega 1 and omega 2 are different, there is no correlation. So in this case, when different frequency components are completely uncorrelated, we find that the intensity at the output port of the interferometer actually becomes time independent. And then one changes the intensity by changing the argument of gamma, the coherence function, or phi k, and then by looking at the variation of intensity as a function of these quantities, they can then obtain this gamma of tau. The second case is when there is perfect correlation between different frequency components, and in this case the cross spectral density function, which is defined like this as an ensemble average, becomes same as the quantity itself, because there is no randomness. Since it is a perfect correlation, there is no randomness at all, and hence the ensemble average is same as the quantity inside. And in this case we saw that the intensities remain time dependent, but since there is a perfect correlation in frequency, there is perfect correlation in time, hence the degree of coherence in this case becomes unity. We also looked at these are the two extreme cases. We also looked at the situation where things can be partially correlated, and we had one example of Gaussian shell model source that we discussed, and with these two cases being the two limiting case of that example. Okay, now we also discussed the concept of coherence time. The coherence time is formally defined in this manner, that is, it's the second moment tau square of this quantity, where this is the autocorrelation function. So, and this is for the normalization. So this is how coherence time is formally defined. Frequency bandwidth, it is defined like this. So this is again a second moment. We also saw that the coherence time times the frequency bandwidth, if it follows an uncertainty kind of relation. We also looked at one very common and useful spectrum, which is the Gaussian spectrum. This is the normalized Gaussian spectrum. For this spectral density, the gamma tau function assumes this functional form. And just for the visualization, if for this one we can see this is the spectral density s omega, this one, and the corresponding gamma takes this form, and the width, half width actually rather, of these ones, the root mean square widths of the spectral density is the frequency bandwidth, and that of the degree of temporal coherence function is the coherence time. So these are the concepts we actually looked at last time. So today we are going to discuss the second order coherence, second order interference in the spatial degree of freedom. So the question is very similar. So now the question we ask in this case is, what is the correlation between field points at rho 1 z and rho 2 z? So these are the two different field points, and at the same time, here we are looking at the same two different space point. Okay, so that's the field coming in, and that's my point r1, which we are writing as rho 1 z, and point r2, which is we are writing as rho 2 z, and then we are asking the question as to what is the correlation between the field vibrations at r1, which is rho 1 z, and r2, which is rho 2 z. In this case, we are interested, just to make things simpler, we will separate the time part from the discussion. So this is this is the generic signal VRT. When we take this Fourier transform in time, that's what we get, and this is the frequency, different frequency component. So this V tilde R omega, that we will call U rho z, where R is simply rho z, and we are not showing this omega frequency here, that labeling. And so this U rho z is essentially the field at rho z at a given frequency omega. So once we know everything about U, then of course we can put it here and do again this omega integral to get VRT. But for this part, when we are studying second order coherence in space, we will only study U rho z. Once we know U rho z, we substitute it in here, and then we can get VRT. Okay, so now as to the answer of this question, now how do we do it? Again, the methodology is same. We take part of the field from this point r1, and the part of the field from this point, and then we combine it at some other point, and then by looking at the intensity at this point, we should be able to get the correlation between the fields at these 2 points. So that's the spatial interference again. Now the field amplitude at rho z, that is observation point, will have a component from the field at rho 1 0, which is z equal to 0 point here, and this is z equal to z point. And of course this is e to the minus I omega t1, because that's the time it takes for light to get here. So that's the phase factor it will get. K1 is the factor because of the this is just a geometric factor because of the size of the slit and how much the diffraction and all. And then it will also have a contribution from this particular slit, which contains this field at rho 2, and of course this phase factor because it travels separate distance than this one. So time it takes for light from here to there is t1, and in this case is t2, and that's what it shows up. So this is the field at U rho z, and it has a components from U rho 1 and U rho 2. Okay, now if we look at the intensity at rho z, so that's this quantity U star rho z U rho z, and if we just calculate it, we find that it has K1 mod square U star rho 1 U rho 1, K2 mod square U star rho 2 U rho 2, and then 2 cross terms. So we see the intensity at rho z has a component of intensity from rho 1 0, in component intensity from rho 2 0, and then the cross term which represents the field correlation between these 2 points. So again we see in the spatial second order interference that by looking at the intensity at the detection point, we are able to obtain the correlation information at the source point. And here we have defined the source point to be the z equal to 0 plane, and the observation plane is z equal to z. Okay, now before we get into the second order interference in space, let's look at some essential mathematical concept. And the first thing, and I will actually just repeat myself here, whatever we did in the case of temporal interference, we'll do exactly the same thing for the spatial, just for the consistency part, and also to show that these things are quite analogous as to how they work. So first is the stationarity, and of course we looked at this concept, and here we are looking at the stationarity in the spatial degree of freedom. That means something that doesn't change as a function of space. So stationarity is defined as when all the correlation functions are independent of the space origin. That means space can be shifted without affecting the correlation function. We can also have the concept of wide sense stationarity, and this means that if the mean and the second order correlation functions are independent of the space origin. So this means if we just take the function, if we just take the field itself, then U rho z, that should be same as U rho minus rho. So if we just shift it by a rho, should not change. That means, and rho minus rho is same as 0. So field at rho should be same as field at origin. So that's the condition on the mean of the field. We take the intensity I rho z, which is u star rho z u rho z, and of course if we shift the phase space origin, things should not change. Hence intensity at rho z should be same as intensity at origin, rho equal to 0 and at z. For the correlation function, we have u star rho 1 z, u rho 2 z, and if we shift both of them by rho 1, that means rho 1 minus rho 1, rho 2 minus rho 1, then it should be the same. And this implies, and again here this rho 2 minus rho 1 we are writing as delta rho. So the Whiteson stationarity implies that the correlation function doesn't depend on the spatial coordinate, and it depends on spatial coordinate only through their difference and not directly to the spatial coordinates. So this correlation function basically depends only on delta rho, which is the difference of the spatial coordinates. Okay, so that's the Whiteson's stationarity. Now when we study the spatial correlation, just like in time when we are studying the temporal correlation function, we saw that it is quite useful to go in the conjugate basis, Fourier basis, which is the frequency basis. Similarly, when we are studying the spatial correlation and field u rho z, we will find that it is quite useful to go to a conjugate and the Fourier basis, which in this case is the spatial frequency basis, and that we will see now. So again at the outset, let me just say that we are interested, usually the coherence theory is interested in the general field, but here we are concentrating mostly on the fields that are beam like and that's going in the positive z direction. And I think as we go on in this lecture, it will be clear as to what is beam like, what does it mean by going in the positive z direction, and so on. Okay, so this is the generic field VRT, and as I said again, as I said in the second slide, this we represent as in the frequency basis in this form, and this is these are the different frequency component. And this frequency component will not show the frequency argument, and this will be our field u rho z. So we are not showing the frequency component, but this means that this is at a given frequency, single frequency. Okay, now this u rho z can be written in terms of a Fourier transform, Fourier relation, and here this is a two-dimensional Fourier transform. R is a three-dimensional variable, but rho is a two-dimensional variable, so R is basically rho z. So xy we are writing as rho, and this as, so this is a two-dimensional Fourier transform. So rho is just xy, and the q, which is the spatial frequency, which is the Fourier, the conjugate basis for rho, that we write as qx qy. And so if we use this Cartesian system, then this same equation we can just write as u xy. I'm using semicolon z just to make sure that for z we are not going to the conjugate basis, just for the xy that we are taking the transform and going to the conjugate basis. So then it is u xy z, u tilde qx qy, z remains, and that's the Fourier cardinal. Okay. So now we know that VRT, this is spatio-temporal signal, this satisfies Maxwell's equation, but this monochromatic component, this actually satisfies the Helmholtz equation. So this VRT, that satisfies the Maxwell's equation. In fact, if we just write Maxwell's equation for single frequency, that becomes a Helmholtz equation, and this is the field at a single frequency, and so it satisfies the Helmholtz equation. Del square plus k square is u rho z. Okay, now before we proceed, let me just give you a pictorial depiction of different quantities. So when we say k, that's the wave vector going, let's say, in some positive z direction at some, this is just some arbitrary wave vector. Its z component we represent as w, and the xy component we will represent as qx qy. And this qx qy, that makes a two-dimensional vector that we will represent as q. So this is q is the spatial frequency basis, this is two-dimensional, k is the wave vector which is the three-dimensional. This wave vector, its magnitude is this k, and this k is connected with the frequency by this formula at omega equal to ck. This k is the three-dimensional vector qx qy and w. We can also write it as qw, and the magnitude of q, will write this as a non-bolded q, and this is basically qx square plus qy square. So I'm just putting it everything in one place so that it is kind of clear as to what do these different symbols actually mean. Okay, so now let's come back to this Helmholtz equation, which is being satisfied by this signal u rho z. So this del square is basically del square del x square, del square del y square, del square del z square plus this k square, and this acts on this u rho z. And for this u rho z, we will use this, I will now use this expression. So that's this expression, so this should be 0. So these will then act on these two quantities. Now this integral here, the variables are qx, qy, but these operators, they are x, y, z, and just k, and we see that there are two terms. So if we just do these operations, this is what we get. So this that's the dqx, dqy. Now each term is acting on this product of these two terms. Now we see that for k square, it won't act on anything, so just k square stays here, that's the first term, and that's the second term. It doesn't do anything. For del square del z square, now this will only act on this term and it won't act on this term. So when it acts on this term, we just write del square del z square, this quantity u qx qy z here, and then this we just separate out. For del square del x square, it won't act on the first term, it will just act on the second term because there is an x here. So if we just do it, so what it gives out is minus qx square. So that's minus qx square u tilde and this exponential term. Similarly, this del 2 by del y2, this will also act only on this one and spit out minus qy square, and so we have here minus qy square u tilde and this exponential term. So this is what we get when we operate with this term on these terms. All right, now so what we have is del square del z square term, and then this qx square minus qy square plus this k square here. So this we can then just simply write this del square, this stays constant, this stays the same, del square del z square, this term, and these three terms we are combining together and writing it as w square u tilde, where w is k square minus qx square minus qy square. So this we are just writing it in the combined form. Okay, now since this entire integral, since this is 0, the only way it can happen is when this term for every qx and qy is actually 0. So this thing being equal to 0 simply yields then that we have to have this thing being satisfied, and this says that u tilde qx qy z has to satisfy this differential equation. Okay, so we started with this v and then vrt, and then we said we interested in only in u rho z. U rho z, we wrote it as a two-dimensional integral where the conjugate base is the spatial frequency basis, and now I find that this component u tilde qx qy z, they satisfy this differential equation, and where this constant w is k square minus qx square minus qy square. Okay, now so if w square is k square minus qx square minus qy square, then what is w? W is either k square minus qx square minus qy square if qx square plus qy square is less than k square, and it is equal to I qx square plus qy square minus k square if qx square plus qy square is greater than k square. So these are the two conditions that we can actually have. Now what is the generic solution to this differential equation? The generic solution we know is of this form, that it is just some quantity qx qy a and e to the I omega z e to the minus I omega z. Now let me kind of point out here that this solution where omega w is actually positive quantity, and so if you see here, if it's a positive quantity, this is a propagating wave solution. So w being positive, and when the general solution is this means that this is a propagating wave solution. On the other hand, when w is complex and we see the general solution is like this, then if you put a complex quantity for w, then it will become e to the minus omega z. So that represents in the decaying wave or evanescent wave solution. So these are the solutions that actually decay very fast. This is also this is not an imaginary solution. This is also a solution, and these as decaying evanescent wave solutions, they actually have a lot of applications in nano optics and near field optics. But here we are not interested in the decaying solution, we are only interested in solutions, the beam like solutions that are going, that is propagating in the positive z direction. So although these are physical solutions, we will not be looking at it, and we only concentrate on the positive propagating wave solution. So if we concentrate on the propagating wave solution, that means we are only taking the positive values of W. So that is the solution that we have. So if this is a solution for u tilde qx qy qz, then the u x y z, this quantity, we can just write as this. This is simply writing this equation with by replacing this u tilde by this quantity. So that's the general solution for u x y z that we have. Okay. Now let me point out that here the spatial temporal field is as VRT, and we have the time dependence of each v tilde r omega or u rho z is this e to the minus I omega t. So implicit time dependence here is e to the minus I omega t. So now we have these two terms, propagating solution e to the I omega z, e to the minus I omega z. We find that if we combine this with this e to the minus I omega t time dependence, then this first term gives me e to the I omega z minus omega t, and this is actually wave going in the positive z direction. And on the other hand, this one will give e to the minus I omega z minus omega t, and this is a wave that is going in the minus z direction. Since we are interested in wave going in the positive z direction, we will only look at this type of term. We will only look at this type of term, which is e to the I omega z minus omega t. So as a result, we will again, this is real, this term is physical, but this is going in the negative z direction, and then we are not interested in that term. We are only interested in things that are going in the positive z direction. So we'll just keep this term, and so if we do that, then the u x y z we can write as like this. So it's just a q x q y, the spatial frequency component, and then this term integrated over dqx dqy. All right. So again, that's the u tilde satisfies this equation, and through the constraint on that equation, we find that this u x y z has this kind of form. Now we see that this is actually not a Fourier relationship. This is because of this presence of this w z, this is actually not a Fourier relationship, but if we look at this equation at z equal to 0, it's actually a Fourier relationship. That is u x y 0 is a q x q y, this quantity dqx dqy. So this is just a very nice two-dimensional Fourier transform. And if we invert it, then we can write a as a Fourier transform of u x y 0. So this is also Fourier transform. So these two are the Fourier transform, and so u x y 0 and a q x q y, they actually form Fourier relationship. So this is same as just like we have time and frequency forming a Fourier relationship, we have this two-dimensional space coordinate and this two-dimensional spatial frequency vector that forms a Fourier pair. All right. So now few things about this A that shows up here. A is called the angular spectrum representation of fields going in the positive z direction. So this going means this propagating in positive z direction means going in the positive z and not in the negative z. But again, let me point out the decaying fields are also physically real fields. Fields going in the negative z direction are also physical fields. But here since we are interested only in the fields propagating and going in the positive z direction, we are taking this form of the field. And this angular spectrum forms a Fourier relationship with this u x y. Of course, this a q x q y, this does not depend on z. This does not depend on z, and in fact, knowing a q x q y, one can calculate u x y z at any z. That means if once we know a q x q y, then we can substitute the value of this in there and then calculate the u at x y z. So let's do that. So this is what we have, the u at any z, and the a we have written in terms of the field at z equal to 0. So now if you want to calculate the field at z, what we do is just substitute this expression in there, and that basically gives us the field at x y at any z. So this a q x q y, when we substitute in here this expression, this is what we get. We can just arrange it a little bit, and so that's the u x y z in terms of u x prime y prime 0. So this is a 4-dimensional integral, but this says if we know the field at x prime y prime and z equal to 0, then we can find the field at u x y at z equal to z. So this is what we have. All right. So next we see this is the actual wave vector, and the two-dimensional spatial frequency with this q is this qx qy. So now suppose we have the situation that qx square plus qy square, that is this mod of q, is much smaller than this mod of k. Okay, so that means this wave is propagating mostly along z. So in that case, this mod is much smaller than k square. In that case, the w, which is k square minus qx square minus qy square, this can be approximated as k minus q square by 2k. Okay, this is called the paraxial approximation. This basically says this is a beam-like solution. This is going mostly along z, and it is just not diffracting too much. So it's mostly a beam-like. For example, when there is a laser pointer, or laser beam is mostly in the paraxial approximation, and it's a nice narrow beam, and that's why we have written that we are interested only in beam-like solution. So for those fields, this condition will always be satisfied, and this is what is called known as the paraxial approximation. Okay, so within this approximation, we can write this u x y z. Now I am writing this as a two-dimensional way. So x y I am writing at rho, z is z, and then on this side a q x q y I am writing as a q, e to the I q x x plus q y y I am writing as e to the I q dot rho, and this w z, this w we are writing at k, I am writing it as k minus q square by 2k. So this k and z gives me to the I k z, that comes out, and this q square by 2k, this comes here. So it's minus e to the minus I q square by 2k z. So this is the form of the field u rho z, which is going or propagating along the positive z direction, and which is within the paraxial approximation. Okay, so this is the spatiotemporal field we have, and this is the individual frequency component, and this individual frequency component can be written as a two-dimensional Fourier transform in this manner, where AQ is called the angular spectrum, and this is written within the paraxial approximation, and this represents a beam-like field going in the positive z direction. Okay, this is the field. So here let me also just make a comment here that things are looking a little different in the spatial degree of freedom than things were in the temporal degree of freedom. That this is because we are handling the space in a slightly different manner than time. In the case of time, we just took a simple Fourier transform t and omega, but in the case of space, we have this three-dimensional space, but we split that as a two-dimensional rho and z, and then take a two-dimensional Fourier transform only, and z stays as it is. So because of that, things are definitely a little different than what they were in the case of time, but yet there are several things that are quite analogous, and then my aim here is to kind of point out all those analogies, so that it looks so that whatever concept we have learned in time, we kind of see that they are also applicable in space. Okay, so that's the form of the field we'll be using. Now we are interested in the interference, spatial correlation. So, and that interference we study through the correlation function, and the main correlation function for the spatial degree of freedom would be the quantity u star rho 1 z, u rho 2 z, and this represents the correlation between the field vibrations at 2 points, that is rho 1 z and rho 2 z. Okay, now given this form of the field, then we can write this correlation function as a two-dimensional or rather four-dimensional integral, and this is an ensemble average. So all these quantities are, I mean, non-random quantities. The only random quantity is AQ, so the ensemble average is only over this one. So we have A star Q1, AQ2, and the remaining ones are like that. This one is called the cross spectral density function, W rho 1 rho 2 z. Now we can write it like this. This AQ1 AQ2, this we write as this capital A Q1 Q2, and this is called the angular correlation function. This cross spectral density function, angular correlation function, these are related like this. And just like in the case of time, when we saw that the temporal correlation function, the correlation function in time and correlation function in frequency, they had a very nice Fourier relationship, which we then call the generalized Wiener-Khinchin theorem, and then normal Wiener-Khinchin theorem. Can we have something similar here? But if you look at it, there is a relationship, but this is not exactly a Fourier relationship here. But we also note that if you look at things at z equal to 0, then this term actually goes away, and then in that case this becomes just this. So W rho 1 rho 2 is A Q1 Q2, this quantity, and then dq q1 and d2 q2. So this is then the exact Fourier relationship. We can see that we can then invert this relationship and write A q1 q2 in terms of W rho 1 rho 2. So this is the generalized Wiener-Khinchin relationship between rho and q, that is a two-dimensional space and the two-dimensional spatial frequency, just like we had the Wiener-Khinchin in between time and frequency. Okay, here we can also define a degree of coherence in exactly the same manner for this W, and the degree of coherence function we call mu rho 1 rho 2, and we are defining it as W rho 1 rho 2 divided by W of rho 1 rho 1, W of rho 2 rho 2, which is basically density, the spectral density at rho 1, spectral density at rho 2. We can also call it intensity, and the degree of this correlation will range between 0 and 1. Okay, now if the process is actually spatially stationary, if the random process is actually spatially stationary, then we saw that the correlation function has to depend on the spatial coordinates only through the difference. So W rho 1 rho 2 has to be a function of delta rho only, and if that is the case, then if you just look at this equation, that if this side depends only on delta rho, so then this side also has to depend only on delta rho, and for that to happen, the only way that can happen is when A q1 q2 has this form, that is SQ1 delta q1 minus q2. And this basically says that if the process is spatially stationary, that means the different q components, they should be completely uncorrelated. This is same as what we had for the temporally stationary process. This is the same condition. Okay, so now if this process is spatially stationary, then this is a condition on the cross spectral density function, and then that constrains that the A q1 q2 has this form, and if A q1 q2 has this form, then this equation we can write as W delta rho, and this side just becomes one dimensional integral SQ1 e to the I q dot delta rho d2 q, and this is called the spatial Wiener-Khinchin theorem. This is the generalized Wiener-Khinchin theorem, this is the Wiener-Khinchin theorem. And this one is the one dimensional, or rather two dimensional, this is four dimensional Fourier transform relationship, which connects the cross spectral density function and this spectral density function. And this we will use in similar manners as we use the temporal Wiener-Khinchin theorem. Okay, so that's pretty much it. The two more concepts that we can discuss. This is exactly analogous to what we do in the case of time, and those are the concepts of space average. So just like time average, we can also have the concept of space average, where if this is the field u rho z, this we integrate over space. This should be minus a. From minus a to a is the area, the large area that we are kind of integrating things over, 1 over 2a in the limit this a going to infinity. So that's the space average, that's how we can define it. And then we can have a similar concept like ergodicity in space, and if a field u rho z is spatially stationary and ergodic, then the ensemble average can be replaced by space averages. So in this course we may not have many occasions to utilize this concept of spatial ergodicity, but this concept is very analogous to what we have in the case of time. So now we will stop here. Thank you.